Okay, so let's try to finish this proof today. So, okay, sorry, I think last time I just stopped at the place where I was about to, yeah, okay. So, okay, if you remember that last time we showed that, okay, so this take a little bit long. So, okay, so we have this projection and then we have, okay, so we have this x hat, right? So which is being defined as, okay, so remember we have two pictures. So the picture I'm drawing is the picture that's stated in the theorem 10.4, corollary 10.4.7. Sorry, and then okay, so here this gamma. Okay, so we take this gamma as a subgroup of the group of the deck transformation of this gamma. Okay, so then this x hat is like the this x tilde quotient by this gamma. Okay, so now okay, so then by so by the previous theorem, right? So by the theorem we proved a while ago, the very long theorem. So which one? I forgot. Sorry. Give me 1 second. Okay, so before that, okay, so here we go. So okay, so by theorem 10.4.6. Yes, but theorem 10.4.6, we get an isomorphism. Okay, so this is okay. So chi composed with chi hat inverse, which is equal to gamma hat. So this is the gamma hat, and then this is covering by the quotient relation by this group gamma, and then we have this. Okay, so we have the gamma hat pushed forward from. Okay, so remember last time we have this base point business, right? So okay, so here we fix the point x naught tilde upstairs, and then we do a projection to drag it down. So this is like the projection of this x naught hat, okay, downstairs, and then we also do the same thing. We also do another projection down here. So this is the space. Let's call this x naught hat. Okay, because this is x hat. Okay, so then which is equal to the group. Yeah, so the quotient map of this x naught tilde. Okay, so then what we get is that we get, so this is gamma push forward from pi 1 of this x hat comma x naught hat. Okay, so from starting here and then to this pi 1 of x naught. Okay. Yeah, so basically, yeah, so this is the push forward map. And then what we have is that okay, so maps pi 1 of x hat of x naught isomorphically onto gamma. Okay, so onto gamma. So wait, sorry. Yeah, I forgot this. Sorry. Okay. So okay, yeah. So this is okay. So we are claiming that this chi composed with chi hat inverse is the same thing as gamma push forward. Okay. Okay, so right now what we have, okay, so what we have is that, okay, so here, okay, in our case, right, so in our case, give me 1 second, okay, okay, so in our case, okay, so let's see what is this chi and this chi hat. So yeah, so in our case, okay, so this chi is from okay, so this chi is from deck transformation group of this vertical gamma to pi 1 of x naught. Yeah, so basically it's the identification of this deck transformation group and the pi transformation group of this x naught. And then okay, so then what? So then okay, so what about this chi hat? Okay, so then for this chi hat, okay, so this chi hat is from yes, so this chi hat is okay, so this chi hat is from gamma hat. Yeah, so this chi hat is actually in our case, because we use this gamma as a subgroup of the deck transformation group of this vertical gamma. So this chi hat actually maps. And then we also show that yeah, so we also show that for each for each of this space, right? So you can so the idea is that if you have any subgroup of the group of sample order, you can always do this. And then you do this quotient map by this relation by this subgroup. And then what you get is that you will always get a, so as long as you satisfy the condition of C10.4.6, you will always get a yeah, you will always get a connectedness, locally semi-connected, locally compact Hausdorff space. And then this mapping is the universal Korean map. And then this the deck transformation group of this Korean is exactly the subgroup that we pick. Okay. So here, here this is equal to the deck transformation of this universal Korean. So let me check. Okay, so okay, yes, exactly. Okay, so now, so this is equal to what? So this is from the gamma to the let me think. Okay, so to pi 1, okay, pi 1 of x hat, x naught hat. Yeah, so basically this is from, yeah, so from the deck transformation group of hold on 1 second. Okay, so from the deck transformation group of this covering map, okay, to this yeah, so to the pi 1 of x naught, sorry, x hat, x naught hat. Okay. So then, okay, so what do we get next? So, okay, so therefore, we have that Okay, so therefore, we have okay, so here we have this kind inverse, right? So we start with this pi 1 of x hat, x1 hat to this group gamma, and then for the wait, pi 1 inverse, and then this okay. Okay. Sorry, I think I said something wrong last time. So, wait, what did I? Sorry. Let me see. Okay, yeah. So, so this gamma hat put forward from. Okay, so let's focus on what we want to show. Okay, so we want to show what? We want to show. Okay, so we want to show that there is a. Okay, so we want to. Okay, so we want to show that this. Okay, so we want to show exactly the same thing, right? So we want to show that this gamma hat push forward from pi 1 of x hat base point x naught hat to this pi 1 of x naught. It's an isomorphism. Yeah, so that's what we're trying to show. So wait. No. This is not what we're trying to show. So we are trying to show that this maps pi 1 of x hat space at x naught hat isomorphically onto gamma. Okay, so what he means by this gamma is, I think it's under the identification. Okay. Wait. No. So gamma is a subgroup of. Wait, I was a bit confused. So gamma is a subgroup of. Okay, so initially this. Okay, so initially. So we know that this gamma is a subgroup of the group of pi 1 of x naught, right? Okay. Oh, I see. Okay. So now, then it becomes a subgroup of the group of. Okay. Deck transformation. Okay. It becomes a. So we realize this gamma as a subgroup of the group of deck transformation of this vertical gamma. Okay. So then we realize. Okay. So we realize. Yeah. So realize this gamma as a subgroup. So then what? Let me see. So why it is becomes a deck transformation of this Oh, okay. So then, for any subgroup of the group of of that transformation, we can quotient by that, right? Okay. So we do another quotient map. Okay. Okay. So I see. So okay. I think that's something else. And then okay. So then what do we want to show? Okay. So we really want to show that. Okay. So go back to the initial condition of this initial condition of this gamma, right? So we want to show that this map. Okay. So this map maps the part one of x hat based at s naught. So what do you want to say? Is it an isomorphism? Okay, isomorphically onto gamma. Okay, so we want to show that it's an isomorphism. Okay. Okay, so we want to show okay. Okay, so what we know is that, so what do we know? Okay, I think I also made a mistake here. So, wait, I don't make a mistake. Okay, no, okay. So, okay, okay, yeah. So this is from this is the result by the theorem 10.4.6, right? So, what was it? Okay. Yes. Okay. Chi-hat is the group. Yeah, I think so. Something's not right. Chi1 on x hat, x1 hat to chi1 x hat. Okay, so first we start with the chi1. Yeah, we start with this one. And then we go to here. Deck transformation of here, and then we map. Oh, okay, I see. Okay. So, okay. Yeah, okay. Okay, so why is that isomorphism? Okay, so shoot. Okay. Yes, it is indeed an isomorphism because so here, okay. So wait, no. We get isomorphism from sorry. Okay, so wait, why is this? Yeah, the question is why is gamma, right? So why is rising to gamma? Okay. Okay. Okay, let's try to show this. Okay, so let's see if we can show this. So, okay, so, okay, so this is definitely true by the theorem 10.26. Okay, so then, so, okay. So with that, so let this R prime be, maybe let's say that. Okay, so I want to say that. Okay, so R raised at small n, then R is R prime. Okay, so I have 1. So let's first show it's on it's induction. So okay, so this implies, okay, so I'll use this here. So this implies that right. So here we have pi of pi inverse of this yeah. Yes, I think we have. Yes, I think this is indeed a. Yeah, my conclusion mainly is that we know that. So, I think in this case, the deck transformation group is a bigger group, right? Because we know that this is the deck transformation of the variable gamma, right? And then this is to pi 1 of x naught, right? So this is the deck transformation group, but this is the deck transformation group of this map. So why they can be composed with each other? So we have input as pi 1 x naught, sorry, pi 1 on x hat, x naught hat. Then you map onto the deck transformation group of this map, of this projection map. Okay. And then you are taking oh okay. Yeah, you are taking the input. Yeah, then you are taking you are kind of realizing this. Okay. You are realizing this as the depth transformation, of x, and then use that as input, and then wait, why is that nice?
I think I need to go back to the proof. Why is that isomorphism?
Yeah, so we input is wait. So I'm sure that this is isomorphism, and then this is isomorphism. Okay. So when you compose with the right, so we compose with this two. It depends on the image set, right? Okay, I think the question for me is that, so why it is, I think the question is that why it is onto, right? So why this map? Yes, so why is onto? So basically that's the question. So so namely if I give any element with power x naught, so why, so I know that there's definitely an element, unique element that in the depth transformation group of this gamma that corresponds to that element, but so but why there is a right? So why there's an element from this chi inverse that would hit this element in this depth transformation group of gamma? So namely why? So so why these two are the same? I think that's my point. I think that's the issue. Okay, so so that's what okay. So why they are the same? Let me see. Okay, so for any element in the depth transformation group, can you okay, so sorry, I was a little confused. Oh! Okay. Sorry. In the theorem, it doesn't say in the theorem that this gamma put forward is an isomorphism. Okay. I'm just thinking, this is an isomorphism, but in the theorem, it doesn't say that it's an isomorphism. Okay, so here, this is the isomorphism. So in this theorem, it says that it is an isomorphism. Okay. So so it is true indeed. It's an isomorphism because okay. Yes, because because this gamma is we show in this we show in part A of theorem 10 of this of theorem 10.4.6 that this gamma is the transformation group of this covering space map. Okay. Yes, from part A. So this is by the part A of theorem 10.4.6. And then we also identify the gamma as so this gamma start with this gamma we also identify this gamma as a subgroup of this Dirac transformation group. So this gamma already is a subgroup of the Dirac transformation group. Okay, it's already a subgroup of the Dirac transformation group. So therefore, there's a So therefore, when you restrict the x, when you restrict the chi, when you restrict the chi to gamma, then it gives you the isomorphism. It will give you isomorphism. Okay. So then yes. And that shows that shows the proof here. That shows the proof. Okay. Yeah. Okay, so I didn't show that it is a unique, right? So I didn't show the uniqueness. So why is it unique? Okay, so here we have that. Okay, so by correlation 10. By correlation 10.2.9. Okay, so correlation. Okay. Sorry. I didn't. I didn't restate what is correlation 10.2.9. So let me. Let me try to say that. Let me try to state the correlation 10.2.9. Okay, so correlation 10.2.9 says that gamma from xn to x and gamma check from x check to x be connected couplings of connected couplings of a connected locally as connected topological space two coverings are equivalent if and only if there exists a point x not check. This is gamma check of gamma check inverse of x naught, such that this gamma push forward of pi 1 of x hat x naught hat is equal to gamma check push forward of pi 1 of x check is an x naught check. Okay. Yeah, so so this is the theorem that we are referring to. Okay, so this is the proposition that we are referring to here. And then so basically it says that if you have two connected covering space of of the same space X, where this X is connected locally castellated to one space. And then we fix the base point X naught. And then here it says and then we take a x naught hat from the fibers under this image of this gamma, and then then we are saying that these two coverings are equivalent if and only if there is a point x naught check in the fiber produced by the gamma check. Okay. Such that the gamma pushover of the fundamental group is the same thing as the gamma check pushover of the fundamental group. Okay. Okay, so here, I think we have it, right? So here we know that, so this is the isomorphism, right? Okay. So now, what happened to our original case? Let me try to think. Oh, okay. Yeah. Okay, so here we okay, so we are trying to show that this cover is unique, right? We are trying to show that this cover is unique. So okay. It is unique indeed. So the reason is that so the reason is that if you have another so if you have another covering, right? So if you have another covering, then it will produce you the same group, right? It will produce the same group. So if you have another covering, let's say some covering let's say another covering. So let's say X check here, and then let's even by yeah. So sorry. So there's a unique. Oh, okay. Yeah, so there is a unique covering space because if you have another covering space such that with the covering map, let's say gamma check. So if you have another covering space, so if you have another covering space from this X check to X. Okay. Such that. Okay. Yeah, gamma check push forward from this type 1 of is an isomorphism. Yeah, so it's an isomorphism. Yeah, so therefore by this proposition, yeah, you will have the two covering as equivalent to each other. Oh, okay, so that shows the result here. Okay, that shows the result. Okay, so okay, yeah. So that finished the criterion for the covering for the yeah. So that's finished result for the Dex transformation group. Oh, sorry, for the Dex transformation. Yeah. Criterion, and then okay, so let's end today. Okay, so let's end today, and then yeah, so let's end today.